Two people watch the same film on the same evening. One of them calls it the best thing they have seen all year. The other one turns it off halfway through. Nothing about the film changed. So a system that wants to tell you what to watch next cannot ask how good a film is. There is no such number. It has to ask a harder question. How good is this film? For you. And it has to answer that for a person it has never met, about a film they have never watched, using nothing but what other people did. Here is how that question gets written down. Down the side, every viewer. Across the top, every film. Each cell holds one rating. When Netflix ran a competition on this problem, their grid had 480,000 viewers and 17,770 films. That is 8.5 billion cells, and they had 100 million ratings to put in it, which sounds enormous until you divide. The grid was 1.2% full, 98.8% of it was empty. This is the math behind. Today, how a computer predicts something you have never seen. So the problem is not really about recommendation at all. It is about a grid with almost nothing in it, and one blank cell you would like to fill. Anna has not watched Pride and Prejudice. What rating would she give it? Every recommender in the world is some version of that one question, asked a few billion times. The laziest answer is the average rating of the film. Take everyone who has seen it, take the mean, and hand that number to everybody. It is not useless. It is just not personal. It gives the same answer to someone who watches nothing but science fiction and someone who watches nothing but romance, which is precisely the distinction we needed. Here is the idea that actually works, and it starts with a claim about people. Nobody really has an opinion about films. People have opinions about a handful of qualities, and a film is a particular mixture of those qualities. If I know how much you like a slow pace, and how much this film has of it, I do not need to have watched anything you watched. So let us be crude about it and use two qualities. Give every film two numbers, how much of quality 1 it has, and how much of quality 2. Give every viewer two numbers as well, how much they like quality 1, and how much they like quality 2. 6 films, 2 numbers each, 6 viewers, 2 numbers each. That is all we are going to store. And now the prediction. Multiply the first number of the viewer by the first number of the film. Multiply the second by the second. Add them up. That is the dot product. The same operation the last episode ended on, and here it is doing something different. Not measuring how close two things are, but predicting a number that nobody has written down yet. Look at what that means for the whole grid. Every single cell is a dot product of one short viewer list and one short film list, which is to say the big table is a product of two thin tables, viewers by qualities times qualities by films. The grid has 36 numbers in it. The two thin tables have 24 between them, and from those 24 you can rebuild all 36. That rewriting has a name, and it is one of the most useful results in linear algebra. The singular value decomposition. It says that any matrix at all, any size, any contents, can be written as 3 pieces multiplied together. A set of viewer patterns, a set of strengths, and a set of film patterns. Not some matrices. Any matrix. There is no exception. Before we use it, it is worth seeing what the decomposition actually means, because it is more concrete than it sounds. Take any matrix and feed it every point on a circle. What comes out is always an ellipse. Always. That is what the 3 pieces are describing. A rotation, then a stretch along 2 perpendicular directions, then another rotation. Every matrix in existence does those 3 things and nothing else. And the numbers in the middle are the stretch. The first singular value is how far the longest axis of that ellipse got pulled. The second is the short axis. So when I say the first 2 account for almost everything, I am saying something you can see. This ellipse is long and thin. Nearly all of the stretching happened in two directions, and the other four barely moved at all. The middle piece is where it gets interesting. It is a list of numbers, in order, biggest first, and each one says how much of the original grid that pattern accounts for. For our 6x6 grid, the first is 18.6, the second is 9.4, the third drops to 1.9, and then it keeps falling. Put those in proportion, and the picture is stark. The first two patterns between them account for 98% of everything in that grid. The other four, all of them together, account for 2, which means we can throw 4 of them away and keep almost everything. That is not a trick that happens to work on this example. Real ratings data behaves the same way, and it is the whole reason any of this is practical. And there is a theorem that makes it more than a good idea. If you keep only the largest few and discard the rest, what you get is not merely a decent approximation. It is provably the best one that exists at that size. No other pair of thin tables of those dimensions comes closer to the original grid. Nothing you could invent will beat it. That result was published in 1936 by Carl Eckart and Gail Young, about 20 years before anyone had a computer to use it on. So back to Anna, who has not seen Pride and Prejudice. Her two numbers are 7.2 and 4.5. The two numbers of the film are 0.42 and minus 0.39. Multiply, multiply, add. 1.2. And her real rating, the one we hid before we started, was 1. From two numbers about a person and two numbers about a film. You may have noticed one of those numbers was negative, and it is worth saying what that means, because it is not a flaw. A positive number says this film has that quality. A negative one says it has the opposite of it. Pride and Prejudice scores minus on the quality the science fiction films score, plus on, which is exactly how a single axis can carry two opposed tastes at once. One number doing the work of two categories, and it handles people who do not fit a box. Cara likes science fiction, but she also rates the romances 3 out of 5, which the pure fans of either side do not. Her two numbers come out mixed, somewhere between the two camps, and her predictions follow her rather than the group she was nearest to. Nobody wrote a rule for that. It came out of the fitting. One thing to be careful about. It is tempting to call the first quality science fiction and the second one romance, and I have been letting you think that. Nothing labels them. The arithmetic does not know what a genre is. It finds whatever directions explain the ratings best, and those directions often correspond to nothing you can name. They are patterns in behavior, not categories in a catalogue. Now the part that most explanations skip, and it is not a small detail. The singular value decomposition is defined for a complete matrix, every cell filled. And we have just spent this whole video looking at a grid that is 98.8% empty. You cannot decompose it. The theorem does not apply. So what do real systems actually do? They stop trying to decompose anything, and they fit instead. Start with two thin tables full of random numbers. Look only at the ratings you actually have. Adjust the numbers a little, so those predictions get closer. Do it again, a few million times. What you end up with looks like the pieces the decomposition would have given you, and the field still calls it SVD. But nothing was ever decomposed. It was searched for. The reason to bother is size. That grid was 8.5 billion cells. Keep 50 qualities instead of 2, and the two thin tables hold about 25 million numbers between them. 343 times smaller than the grid, and it can still answer for any pairing, including the ones nobody has ever rated. In 2006, Netflix put $1 million on this problem. Beat our own system by 10%, they said, and the money is yours. They released 100 million real ratings, and for 3 years it was the most public machine learning contest in the world. Teams merged, leaderboards churned, and in 2009, a combined team took the prize with an improvement of just over 10%. And Netflix never used it. The winning entry was more than 800 models blended together, more than 100 algorithms tuned across 3 years for one number on one leaderboard. Netflix looked at what it would cost to run that in production, weighed it against the accuracy it bought, and decided it was not worth it. The prize did change the field. The winner just never shipped. There is a second reason it would not have shipped. That competition was about predicting star ratings, and Netflix does not have star ratings anymore. They removed them in 2017. What a modern system uses is what you actually do, what you finished, what you abandoned, what you watched twice, at what time of day. Far more data, and much messier, but the shape of the mathematics underneath is the same. It fails in ways worth knowing. A brand new film has no ratings, so it has no numbers, and the system has nothing to say about it. Popular things get recommended more, which makes them more popular, which is a loop the arithmetic will not break on its own. And most importantly, nothing here measures whether something is good. It measures whether people like you liked it. Those two come apart more often than you would hope. So, a grid with almost nothing in it, a claim that people respond to a few qualities rather than to films, 2 thin tables found by fitting rather than by decomposing, and to predict a rating, 1 multiplication per quality and a sum. The catalogue changes every week. That arithmetic has not changed since 1936. Thank you for watching. Subscribe and see you in our next video.